good evening, afternoon, and potentially morning to some of everybody. Just to make sure you guys can see the slides.
Sorry.
Anybody?
We absolutely can, and we can hear you just fine. Thanks, John.
Perfect. All right. So I got sort of re-invited to talk at the last minute, so I decided to go with the most vague, buzzwordy, entertaining title I could come up with for parahydrogen related work, which is that we'll be talking about entanglement-enhanced NMR at zero magnetic field. This is work done at the Helmholtz Institute in Mainz with the Diva Bookers group, and in part of this ZULF NMR training network from the Marie Curie. Oh, apparently advancing slides is not allowable. Okay, there we go. In general, the work that we've done has been sort of an interdisciplinary approach between physics and chemistry. Physics gives us the precision measurement tools. Chemistry gives us the ability to design and tune samples. And on both sides of this, we end up being able to spin that out into applications. I should disclose in the meantime, as Boyd mentioned, I now work at NVision Imaging Technologies GmbH. Everything that I will be talking about today is going to be work that came from Mainz, maybe in one or two cases, work that came from Berkeley. NVision is a company that works on spin polarization enhancement and quantum sensing. We like to refer to it as a quantum medical company. We're still a little bit in the secrecy phase, so that's about as much as I can disclose. But keep on looking forward for exciting stuff. So I'll talk about more or less three things today. First one is going to be zero field NMR. Then when I say entanglement-enhanced NMR, I of course mean parahydrogen-induced polarization, and then efforts to get into steady state polarization, just continuous polarization experiments that are particularly interesting for fundamental physics. So that will be about SABRE. So zero field NMR. On the one side, it's okay. Why do you want to do it? Partially, it's fun. It's new. It's different. Also, it allows you to avoid having to deal with these big, heavy cryogenic magnets that you have to fill with helium. If you're a graduate student, that takes up 1 day out of your week. It's a pain. Portability is dramatically enhanced, at least in principle. You can get significantly improved coherence times because you have a very high absolute magnetic field homogeneity. High field, you're always thinking about relative field homogeneity. At zero field, you can really talk about what is the strength of that field gradient. And when you're getting close to zero, it's a lot easier to get exactly zero than it is to get exactly 20 Tesla across your sample. You can also see through metal, and you have a different symmetry relationship that's going on. You no longer have this one axis that defines everything defined by the magnetic field. You get to see things sort of more in the natural environment of spin-spin interactions. So again, I'm jumping through things a little bit because I'm assuming that most of the audience is familiar with NMR. Let's look a little bit about why we usually use high fields. On the one hand, we like to have chemical shift resolution, especially the chemists amongst us, and vastly more so the biologists who want to look at big proteins and so on. Those who got a higher field, chemical shift dominates. That's quite handy. Also, your equilibrium spin polarization improves more or less linearly at convenient temperatures. and the sensitivity of inductive detection, that is detection with coils, which is what lives inside of your NMR probe, that goes up not quite linearly, frequency to the 3/4 in the higher frequency regime when you consider the increased resistivity. But again, that's just going to keep on increasing as you go higher and higher field. And in fact, inductive detection as a way of sensing magnetic fields, it's often hard to beat. So then the question that one might reasonably ask from somebody who is talking about zero field NMR is, okay, well, how do we get around this? Instead of chemical shift resolution, we rely entirely on spin-spin interactions. It's not quite as straightforward in analysis for people that like a nice linear relationship between electronic structure, electron density, and chemical shift. But we have computers now, so it doesn't have to be done by hand. Instead of equilibrium spin polarization, as should be perhaps expected in this conference, we have to rely on non-equilibrium spin polarization, because even then, equilibrium is pretty bad. Instead of inductive detection, we use non-inductive detection. The way that we do that is traditionally using alkali vapor magnetometry. In this slide, I'm talking about the case of rubidium. You can simplify things by neglecting nuclei, which is against my instincts. But basically, you just apply optical pumping. You end up with a polarized volume of alkali atoms. And as they process about any magnetic fields that are present, they will induce rotation of linearly polarized light. So you can actually use optical detection to measure magnetic fields. This works at also very, very low frequencies and very, very low fields. And you can go through, you can build things, you can buy a shield, you can engineer a bunch of stuff. Or alternatively, what's really nice in recent years is you can just buy commercial magnetometers that are remarkably sensitive, especially for something you can buy off the shelf. They're at the 10, 15, 20 femtotesla per root hertz sensitivity, which I will admit pales a little bit in comparison to inductive detection at a gigahertz, or even a few hundred hertz, or a few hundred megahertz. But they're really, really quite good. And you can measure, especially in the case where you have a hyperpolarized system with more than enough sensitivity. And it's also relatively inexpensive and relatively compact. Warren was talking earlier, he didn't mention the wooden stool today, so this joke's a little bit out of place. But it costs a little bit more than that. A lot of the cost is in actually the magnetic shield and in the cost of the magnetometers. Electronics you can build yourself. We use some fancy amplifiers that were not really strictly necessary. You can get by with quite a lot cheaper options. The bottle opener adds a relatively additional cost, but compared to high field NMR, you have a lot more options. So the way that for a long time we had been running NMR experiments at zero field is that we would just stick a big magnet on top of the shield. 1.5, 2 Tesla permanent magnet, let the spins reach equilibrium in there. You get some polarization. You drop the field down. Say if you go adiabatically to 0, then you can apply a pulse, and this will induce coherence where you have proton and carbon polarization beating back and forth, which is happening at the J coupling frequency. If you have more than 2 spins, it gets a little bit more complicated, but again, you just add up your angular momenta and you can understand the spectrum reasonably well. If it's a small number of spins, it's pretty easy. When you get to a lot of spins, you need more computer time or a little bit more intuition. So this works. We've been doing it for a while. this is one of the first talks where I've not been showing the spectrum of benzene, but there's a very beautiful spectrum that you can get out of here. The issue is that even though what I was just describing before, where we shuttle from high field down to zero field, is technically non-equilibrium spin polarization, it's still not very good. And if you think about this, the equilibrium spin polarization, it's close to what one could reasonably define as nothing. If you think about the temperature times the Boltzmann constant divided by h, talking about 6 terahertz. So with 600 megahertz, say proton low more frequency, you get around 10 to the minus 4 polarization. If you think about a proton carbon J coupling, again, we'll just imagine a 2-spin system. We're talking about 2 down 10 to the minus 11. And so if I have a whole bunch of, say, acetonitrile, I've got something times 10 to the 21 spins. And actually the square root of that suggests that actually the thermal polarization at zero magnetic field is equivalent to the spin projection noise. The uncertainty, or in other fields, the stochastic polarization of nuclear spins. So literally the smallest thing that could be present before it gets overwhelmed by just statistics. So what we need is a purer state. It's in many ways NMR it's halfway a very quantum mechanical field, and in terms of what the capital Q quantum people would say, it's a very, very non-quantum field. We need to get a little bit more in the direction of the latter. So that's where our entanglement comes in. Again, I strongly suspect that everyone at this conference is probably pretty familiar with how parahydrogen works, but in case somebody's watching on YouTube, I'll leave this slide available. As we know that if you look at the symmetry and antisymmetry of different components of your possible hydrogen states, the ground state, which is the lowest rotational state, must necessarily be antisymmetric in nuclear spins. And because hydrogen is so light, the separations between these states are actually quite large in terms of temperature. So you can very easily cool down such that the equilibrium state would be para. You do this in the presence of a catalyst, you cool it down, you get pretty comfortably 50% para enrichment. You can go much, much higher. And again, because it's spin forbidden in the absence of a catalyst, it stays for a long time. You can then add this parahydrogen, which provides a pair of entangled spins into another molecule. In the case of PASADENA, you end up with this alpha beta beta alpha state and your typical antiphase spectrum. For the sake of historical relevance, have to mention Russ and Dan, the work that they did in PASADENA about PASADENA in '87. And you can also do it at whatever field you feel like. At zero field, it works pretty well. Think about parahydrogen, you have 2 spins, you have a singlet, you have a triplet. On this energy scale, I'm ignoring rotational states. This is purely spin energies, otherwise it would be impossible to see. Then if you imagine that you then add this, so you have an additional carbon coupled in, instead of it just being a singlet and a triplet, and you have a doublet, another doublet, and a quartet. And the distribution of spin states is highly non-thermal. If it's just a 3-spin system, you get 3 peaks at zero field. In one of our favorite cases, we used dimethylacetylene dicarboxylate to then produce dimethyl malate. We get just enormous signals. We were approaching, this is again natural abundance, where we started to approach the limits of our analog to digital converters. So we would actually be in the regime where we would have to start putting resistors in series with our detectors to make sure that we can actually still measure signals. And the signals are enormous. Again, I was talking about sensitivities on the range of 10 femtotesla per root hertz. We get signals of 10,000. And then furthermore, they're, so in the, okay, great signals are good, but signals will be even better at high field. It's also worth considering what zero and very, very, very low field NMR can provide. And so practically, one real advantage is that you don't have to worry about susceptibility. If you have a heterogeneous sample at high field, you have susceptibility induced gradients because different values of mu are going to give you different magnetic fields, and you're going to have gradients in between there. However, if you multiply any number by 0, you still get 0. Everything goes away. And also the low frequencies that we operate at, which are audio or sub-audio, have no problem penetrating metal or conductive samples. Skin depths are millimeters, centimeters, depending on the material. Classic example, a favorite paper of mine as a graduate student was when they took a bell pepper and stuck it into a Coca-Cola can, doing a little bit of low field MRI with squid detection, and you can see it right through that Coke can. Bad things would probably happen if you try to do that at higher field with conductive detection. And also, Michael Taylor showed nicely that if you take a sample that's in the tube or a sample that's dissolved in these polymer beads, you still get a pretty dang narrow peak. So one application that we looked at with this is sort of catalytic reaction monitoring. Naturally, we cheated by using Parahydrogen. So we're looking at, again, starting with this was dimethylacetylene dicarboxylate to produce the malleate and then the dimethyl succinate. And we performed this while bubbling and inside of a metal tube, metal reactor. Admittedly, we had to make it out of titanium because the steel that we had was a little bit too magnetic. It's probably ways around that. But again, try sticking a titanium tube into your NMR at high field and see what you get. As I was saying, there's our reaction. This work was carried out by Dudari and James. Dudari was visiting from Novosibirsk, and James was with us then in Mainz. And you can very easily resolve malleate, succinate. And again, if you try to do continuous bubbling, you're going to have a heterogeneous mixture. If you try to do this at high field, you get a big blob, which is something. Even if you do stop flow, but you still have a tube inside of there, it's hard to shim. You get, resolvable blobs. There's still information in there. However, if you compare the stop flow glass tube at 0 field and a continuous bubbling case instead of a metal tube, they look about the same. In fact, actually, the spectrum has a little bit less of this random noise coming in for no really good reason. But you have a lot more options. And part of our motivation was we wanted to see what happens if we go to higher and higher pressure. If you keep on cranking up pressure on your glass J. Young tube that's designed for vacuum to 1.5 bar of pressure, some of them survive, but a lot of them break into a million pieces. So looking at a metal container is actually quite nice. And in terms of, real industrial chemistry, higher pressures, higher temperatures are really advantageous. our next goal goes, the motivation was a little bit more esoteric, if you will, coming from the realm of dark matter. As the organizers know, it's become physically impossible for me to not mention dark matter in a talk, which in this case is actually especially appealing because, as Professor Snow mentioned, the problem of the combined charge parity reversal symmetry, and trying to understand how the universe and particle physics works. As we've observed in a lot of experiments, the charge parity violation in the universe is not strong enough to explain, or in the current universe is not strong enough to explain how we have so much matter and not enough antimatter. An alternative possibility is that actually this charge parity violating term in the strong force Lagrangian has varied over time. So in other words, you can, if you're a theorist, you can promote this parameter into a field that can change in time. So in the early universe, we had a lot of charge parity violation. Later on, it's relaxed to a state where we have much, much less. Actually, in the field that is produced is referred to as the Axion. And as the energy in this field goes from high to low, you end up actually producing excitations of the field, which are referred to as axions. And allegedly, if you do the math, the amount of axion matter that could be produced in this process more or less corresponds to the amount of dark matter that's observed in the universe. So it has the advantage of actually potentially answering two questions if we can figure out whether these axions are real. And the really nice thing for those of us who are NMR enthusiasts is that these axions actually couple to nuclear spins. And the way that they do that is through, for example, the gradient of this axion field coupling into nuclear spin vector. So you end up with some, I dot velocity or I dot momentum technically. If you then think about how the Zeeman interaction works, I dot B, we can just start renaming things because, hey, vectors are vectors. And we can have the sort of pseudo-magnetic field produced by dark matter in the universe. This is, of course, called the Cosmic Axion Spin Precession Experiment, or CASPER for short. And basically the idea is that you have a dark matter field that can drive spin precession when you're on resonance. Depending on how much polarization you have, this gives rise to some precessing magnetization, and then you can detect this with some sort of magnetometer. At low frequency, an atomic magnetometer works nicely. At higher frequency, eventually inductive detection is your best option. But the real idea is that you basically use a nuclear spin target, if you will, to convert this dark matter pseudo-magnetic field into a real observable magnetic field. And the key thing for this community is the amplitude depends on the nuclear spin polarization. So the amount of amplification that you're actually getting out of this transducer entirely depends on how polarized your spins are. So in principle, you can actually work with just single shot parahydrogen measurements. The problem is that you need to average for a while. You have to deal with systematics. You have to address the fact that the Earth is rotating and there's potential dynamics of this dark matter field. There are streams going through the universe, and more importantly, the galaxy, I should say. So you can't measure for a couple seconds and call it good. You need to be able to measure for days, weeks, months, years. Now is a good time to start potentially feeling bad for the graduate students who have to work on it. But again, we want to have something that can actually work for a long time. We need to do long experimental runs. So one potential opportunity is SABRE. These are some old figures from back in the grad school days with the fearless conference leader, Thomas, where we showed that you can actually do SABRE at 0 magnetic field, in this case for pyridine, and get enhancements of 10,000 or so. But again, those experiments still didn't last that long. So we put together some efforts to try to see if we could make things go longer and to optimize things sort of in situ. So the paper that we it was recently published, we showed that you can use 0 field detection to measure without having to leave the shield. And actually, you can extend the lifetime of the experiment by pre-saturating your parahydrogen gas with whatever solvent you're using for your reaction. In this case, where we're looking at sort of the normal iridium imez catalyst and pyridine, we're doing this in methanol. So we just had effectively boiling methanol that we pass our parahydrogen through so that we could keep the reaction from, in so many words, drying out. Basically, the idea is that you just have some field applied as you are bubbling your parahydrogen. Then you just turn the field off, and then immediately any nitrogen magnetization is converted into a some set of nitrogen proton coherences. So as you vary that preparation field, you then look at the amplitude. I think in this case, we just looked at the amplitude of this biggest peak and varied the field for this preparation through 0. And we saw that usual shape that is always reported in SABRE-SHEATH. What was nice is that there was no uncertainty related to moving the sample from the shield into a high field magnet, or again, to me, high field means Earth's field. So even moving from the shield into a benchtop magnet. And actually, if you look at this fit and these little green lines on the side, that's the 5 sigma confidence band for our fit. So we can be remarkably confident in the fit parameters.
Hey, John, we're about out of time. I'm sorry to interrupt.
Perfect. And so we see that this is actually not some dispersive Lorentzian, but in fact 2 antiphase Lorentzians, where the optimal field is about 0.2 microtesla, and the width of each of these peaks is greater than 0.6 microtesla. And again, remember those optimal offsets that Warren was talking about. Even though you might see that the best polarization comes a little bit higher, the actual level crossing happens at a lower field. So we actually have a significant amount of interference. And in fact, there's a factor of not just 2, but more of closer to 4 polarization that is potentially achievable with SABRE. Stability could use some work. We want days and weeks. We had a few hours of measurements consistently. I think other people will be talking about interesting possibilities later on this week. We had one idea. We'll see what ends up working out nicely. So in summary, ZULF NMR is a thing, and PHIP helps a lot. Thanks everybody involved. And please check out other exciting talks that are coming from the group in Mainz later on this week.
All right. Hey, thanks so much, Jonathan, for an awesome talk. We do have questions, and I'm going to try to run through a few of them. First one from Stephen. At about what, Stephen DeVince, I should say. At about what frequency would you say vapor cells and inductive detection are effectively equal or a wash?
Roughly a megahertz.
Okay, good. Here's more of a just a point from Warren. Good to see that our wooden stool has achieved scientific immortality. Of course, the point is that the basic idea is, if the basic idea is cheap, you can then improve the apparatus as you have done without worrying about cost. So
it's still pretty cheap to screw a bottle opener into a stool, I think.
So that's a good point. I have one quick question about the CASPER approach. Is there any expectation that one isotope might be better or more sensitive than the other, or do you think the higher the gamma, the better? Like, how should one think about it?
So it depends on the coupling. For the coupling that I was talking about there, which is what we affectionately call the wind coupling or the gradient coupling, higher the gamma, the better. There are other expected couplings. Again, the whole point of the Axion is to have to break CP. So as a result, it actually can also induce an oscillating nuclear electric dipole moment. And there are other experiments, especially being carried out in Boston, that are looking at this. In that case, the higher the Z, the better.